Okay, welcome all to, I guess we are wrapping up already the third week of the semester. Wow, okay, we got like 14 or 15 weeks and this is the third week. I'm still in the preliminary stages of the course material, which sounds like, pre-course material. We said, linear algebra is a prerequisite, but we're just covering linear algebra right now. That's what we started this week on Monday, and we're going to do more linear algebra today as well. And today the breakout session, Mihir tells me, is also going to be about linear algebra and also closed form solutions to machine learning problems using only linear algebra. So when there is a simple solution to these problems, the kind of machine learning we need is a fairly simplistic mathematical solution based on linear algebra alone. But I think that's a good foundation. I'm assuming that machine learning is going to be the future and that you are here to be part of the future. And many of you are probably specializing in machine learning and so on. And so what better way to get started than getting your foundations and your principles right? So linear algebra is one of those to get it right. To be able to read a paper on machine learning, for example, any paper on machine learning you pick up will have equations, right? I tell my PhD students also, where are your equations? So you need equations in machine learning. It's like a mathematical subject. And so we might as well, get used to it and relearn these things. Okay, so that's what we're doing this week, still linear algebra. And what have we done on linear algebra is we looked at basics like vectors, scalars, vectors, matrices, tensors, matrix multiplication, matrix inversion, and very quickly, matrix multiplication is all that goes on in what's called as a neural network. You have an input in the form of a vector, you multiply it by a matrix, it converts it into a lower dimensional vector, multiplied by another matrix, it becomes an even lower dimensional vector, and so on. You reduce the amount of information so that you can finally bring it to a state where you can do some simple classification that's going to go on using softmax, something like that. And another use of matrix manipulation is in the problem of linear regression. And I understand today, Mihir is going to show you something in your breakout rooms. One of the questions is about linear regression, where a closed form solution will, for linear regression is a problem of taking an input, predicting the output, some kind of a mapping from input, and the output is some continuous value, and rather than a classification. And so to solve the problem, given a set of samples for these inputs, these were the outputs. Now figure out what should be the function that's going to map it such that you're going to get more or less the right output. And that problem, if you're going to solve it using sum of squared errors, that is, you take a look at all the outputs that you're currently getting with the current set of values, you want to minimize that quantity, and one can show mathematically, which we'll do that when we start linear regression, I think next week, that it actually turns out to have a very simple form where we have a design matrix which consists of, whose rows consist of the samples and whose columns consist of the feature values. That has to be inverted. That matrix has to be inverted using some pseudo inverse, and then you would multiply the vector of outputs for all the samples, and that gives you the weight vectors, how you're going to weight all the inputs and add them all up to get you the output. So that's a simple exercise in linear algebra. So you're going to need to know what is meant by inversion and so on. So those are a couple of examples, and then also a few more sophisticated methods are based on linear algebra, like principal components analysis is based on linear algebra. And also we encounter in linear algebra two things of taking a matrix, could be a design matrix or another matrix of weights. There are different kinds of matrices we encounter. One is a set of, it's a matrix of weights in a neural network, or it is a design matrix. And we do things like eigenvalue decomposition of this matrix, or we do a singular value decomposition of this matrix. There are two different things, which say somehow we obtain the matrix in a particular form of a product of three other matrices, the middle of which is a very simple diagonal matrix. And it contains all the interesting, rich information in a more compact way. And that is kind of the principle of, latent representations, they call it. And so when we talk about singular value or first of all, eigenvalue decomposition involves eigenvalues, eigenvectors. And then singular value decomposition is slightly more general and more powerful, which is the sense of things like recommendation systems, such as I talked about briefly last time, I believe, where we are trying to recommend to somebody as to what they might want to buy or see or so on a social network, based on a simple idea of a singular value decomposition is placed directly into it. So what also happens is machine learning is not just linear algebra. It turns out there are linear algebra solutions, but a lot of these solutions are not practical in terms of large numbers of samples and large numbers of features and so on. And we need better solutions. And it turns out things like neural networks and so on perform much better, where we worry about not just a matrix multiplication, but we have what are called as activation functions like the sigmoid, or and then we have operations like the softmax and so on. All of those have to come into play. And there are specialized types of matrices, which are not full matrices, but repeated use of a small matrix called a kernel, which leads to a convolutional neural network and so on. So there are all these kinds of things. So it's worthwhile to kind of get a firm foundation on these topics. Okay. All right, then I'm going to share the my PowerPoint on linear algebra, and so that's where we're going to go back. And of course, we did half of it. I didn't do the other half. See, what's going to happen here is sometimes I cover some of those slides and then we run out of time. And sometimes I say, okay, maybe you can read on your own. And then I go on to the next topic. But this linear algebra, I could have done that. I could have said, well, we finished one half on Monday. So I was looking at it, debating, should I do the second half of the slides or should I just go on to the next section, which is on probability? But I thought maybe it's worthwhile to cover this second half of linear algebra also myself in class. So because it has got these things about the methods I mentioned, you know, the singular value decomposition and some of which are a little more subtle, and the PCA and so on. All of this come into the second part, which is a bit harder than the first part. I said, okay, let me cover that a little bit. Slides are fully explanatory, and so I'll just give you the main ideas, and you'll have to pore over it yourself. This material that I am going over, this linear algebra for machine learning, is not covered in this kind of depth in many of the introductory machine learning books. They're saying, okay, they put it in an appendix and say, okay, you go and read about linear algebra and come back and then you should be able to follow what we're talking about. But what has happened is, other than these introductory textbooks on machine learning, including Chris Bishop, he doesn't have an early chapter on linear algebra. I think it's in his appendix. Similarly, Murphy's book also has it somewhere in the appendix. And there's so many textbooks on machine learning. Even Tom Mitchell's older book on machine learning does the same thing. But lately, the importance of this kind of linear algebra is being realized, and at least the book on deep learning devotes a whole chapter saying you better study this stuff because it's going to be appearing throughout deep learning. So if you're going to be a deep learning expert, you're going to need invocation of all of these ideas and so on. So you won't find it in the introductory machine learning courses. My slides are kind of a collection of material from various sources, but primarily from the deep learning book. But we are not doing too much deep learning in this course, but the linear algebra remains the same. Okay. All right. So let's just go to the slides again. Also, I'm trying to be disciplined and put the slides and the video recordings online for you. And so you should be able to find the slides uploaded into UB but they're also available publicly, as I mentioned before. You can look ahead as much as you want as to what all this material is. You can find it there, but I try and pull in only the things that we're covering in the course here into UB and then after we finish the Zoom session, I try and upload the video file also there. And I think Mihir is also doing the same thing for the discussions you're all having. Okay, all right, so that's about the various bookkeeping things. And all right, so here we have linear algebra for machine learning is the topic. And okay, all right, so let me just go over the contents which we have done already. So what is all in this chapter again is all this type of stuff. So we finished about half of all these material last time. I think we went up to special kinds of matrices and vectors. I think we probably even covered norms, and then the remaining is the other half, which is eigen decomposition, singular value decomposition, Moore-Penrose pseudo-inverse, trace operated principle. Okay, so that's what it is. So anyway, they're all hopefully defined on all of these slides for you. And yeah, we did an example of flow of tensors in machine learning. We looked at a picture of a cat and how it's recognized by matrix manipulation in a neural network, matrix multiplications. And we talked about a matrix inverse and solving simultaneous equations also we talked about. And all right, let's look at this. I think we looked at this also, a system of linear equations and linear regression, where we end up with a formulation like this. Phi is the design matrix whose rows correspond to samples, columns correspond to features, and W is the weight vector that we need in linear regression. Linear regression is only looking for a bunch of weights. If you have a bunch of inputs, what should be the weights that's going to multiply each of these inputs so that you can add them all up, and that's going to be the value of your output. And in this case, T output is target is T, and it's a vector of values corresponding to a set of inputs captured in the design matrix, and W is the set of weights associated with all the features. And so that is a kind of a formulation of a system of linear equations in linear regression. And the closed form solutions is if that is the formulation, matrix invert, take that phi matrix and you invert it. In this case, it's shown as A here. So you need to invert it. And so that's matrix inversion is one solution. The other one is Gaussian elimination is the other. It's a famous algorithm. If I give you a set of simultaneous equations, actually regression can be thought of as a set of simultaneous equations. We have a bunch of inputs to be multiplied by weights. For example, 1, 3, and -2 are the weights for the first equation here. 5 is the desired output. And so we can regard it in this way. Or we can regard the other way, that the other values are the weights and we are looking for X, Y, and Z. Maybe that's the way to look at it, is we are looking for X, Y, and Z. So that's the solution to the problem. So what are the values of X, Y, and Z, which are common to these three equations? What are their values? So this is solving a set of simultaneous equations. So how do you solve a set of simultaneous equations, right? If you have two equations and two unknowns, you know how to solve two simultaneous equations, right? Some basic algebra would do that for you by eliminating one of the variables and so on. But when you have three equations and three unknowns, or four equations and four unknowns, or 100 equations and 100 unknowns and so on, you can use Gaussian elimination, which tells you how you could possibly come up with an answer. But even that becomes impractical when these things become large, when the number of equations is not the same as the number of samples, all that issues come into play. And so those are closed form solutions, and some of these closed form solutions have disadvantages, numerical instability and order n cubed with Gaussian elimination. So there are all these issues. And though there are, this is just an interesting mathematical slide. This is how many solutions for Ax equal to B exist, and so on. So let's not spend too much time on that one. Span is not all such an important concept of a set of vectors, but it does occur in some definitions. So this is all a kind of a listing of some other matrix concepts. And matrix must be square. Conditions for a solution for Ax equal to B, matrix must be square, m equal to n, and all columns must be linearly independent. So there is if the number of equations is larger, n is greater than or equal to m, then there are some conditions, necessary condition and sufficient condition, so on. For non-square and singular matrices, methods other than matrix inversion are used. Supposing I have small non-square, in the sense the number of samples is different from the number of dimensions. So if you have 1,000,000 pixels, we don't have 1,000,000 examples. We only have a few thousand examples. Then we don't have a square matrix. So what do you do with that? So there are some of these solutions that we need to look at. The pseudo inverse and all these come into play. Here is a more concrete example of linear regression. Okay, this is an example pertains to students in class. The design matrix has n samples and d features. Here is an example of 3 samples and 3 features. The 3 samples correspond to student number 1, student number 2, student number 3. And somehow the teacher has got hold of number of hours studied, number of hours playing games, and number of classes missed. All right. So student number 1 studies for 10 hours, I guess per week maybe, or per day. It couldn't be day, right? It's got to be per week. And then spends 3 hours playing games and did not miss any class. Well, grade was 87. Student number 2 studied for, I don't know what, 6 or 8 hours. And then the number of hours playing games was 20, all right. And number of classes missed was 2 and got a grade of 75. And student number 3, 5 hours studied, 1 hour playing games, and I guess all work and no play makes Jack, right? So we don't want it to be a dull boy here. So some playing is needed, and so this is 5 classes missed, gets 63. All right. So anyway, this is a regression problem that if I tell you I got a new student X here. This is the number of hours studied. It's the number of hours playing games and number of classes missed. What will be the grade of this student based on this? So this is a linear regression problem. This says how much should we weight number of hours studied? How much should we weight the number of hours playing games? How much should we weight number of classes missed? So that we get as close as possible to 87, 75, and 63 for these 3 cases. This is a problem. This is called, we refer to this as a regression problem. Linear regression would be to simply multiply these by weights, so it becomes a linear problem. It's linear in the inputs and linear in the weights. And we say that this feature vector has 3 dimensions. So it says there are 3 features. So this is exactly the design matrix. 10, 3, 0, 822, 515 is the design matrix. And as I mentioned earlier on, some solutions to find the weight vector would be to invert this design matrix, all right, and multiply it by these quantities to get your answer. All right. Anyway, so I think Mihir is going to walk you through that and see how you could do that in your breakout session. All right. So I guess that's about the regression problem. All right. I guess my next slide is about norms used for measuring the size of a vector. And this keeps on appearing frequently in the machine learning literature. And particularly in the deep learning literature, you end up talking about norms map vectors to non-negative values. So if I give you a vector such as x equal to x1 through xn, and we say a norm of this vector x, we just saw an example of vectors, right? We saw 3 vectors corresponding to 3 students in the previous slide. And we say the norm is a function f that satisfies these quantities. This function is applied to x. If it is equal to 0, then x is equal to 0, okay? Which means the vector is a 0 vector, all elements 0. F of x plus y is less than or equal to f of x plus f of y, called the triangle inequality. And for all alpha, for all coefficients alpha, f of alpha x. It looks a bit obtuse here, but it's a fairly simple concept. The next slide, I think, illustrates exactly examples. The LP norm is to take each element of the vector, take it to its pth power, and add that up over all the samples, and take the pth root of it. That sounds terrible. Pth root is called the LP norm. But more understandably, the L2 norm is very simple, called the Euclidean norm, which simply says, take the sum of squares of the components and then take the square root of the sum of squares, which is exactly what we do, right, with finding the distance between 2 points on a plane, right? That's got a name. It's called the Euclidean norm. We think of it as the distance between 2 points is a square root of the sum of squares along each component by Pythagoras Theorem, right? So we say the distance between the origin and this point over here is, if you know x1 and x2, the values of the 2 coordinates, then you take the squares of these 2 coordinates, add them up, take the square root of it. That's the Pythagoras theorem, which says that is the distance between these points, right? The square on the hypotenuse is equal to the square on the sides. That's the Pythagoras. And so, so that actually corresponds to the L2 norm. The distance between this point and that point, between the origin and this point, is given by the L2 norm because it involves squares. But we could also define L1 norm where we simply add x1 and x2, absolute values that is, and then we're putting p equal to 1 over here. And that is simple. And then 1 over p is going to be exactly equal to 1. So this simply says take the sum of the values along each dimension, which becomes exactly what we call as the Manhattan distance or the block distance, right? You know, when you're walking on a grid in a city like Manhattan, or perhaps most cities have these kinds of grids, and somebody asks you, how far is I don't know, the movie theater from here? And then somebody answers, oh, that's 2 blocks from here or 3 blocks from here. So that's they're using basically an L1 norm, which says 1 block this way, 1 block that way, because you have to go along the avenues and the intersections in Manhattan. And so we say that is 2 blocks, right? That's L1 norm. We call it an L1 norm. L infinity norm is an interesting one, which simply says take the maximum of all of these values, and that is the distance. So it's called max norm. I haven't encountered max norm that much. L2 norm is mostly what we use in most of machine learning. L1 norm, sometimes there are a few uses for this thing. And use of norm in regression. Okay, this is where we introduce the linear regression problem more formally. And I think Mihir will appreciate that I'm going over this now because I think he wants you to do something about linear regression. I'm going to introduce the problem here, so it makes his job a bit easier. So we have X is a vector input. Oh, okay. It's not just a single value. It's a vector input. W is a weight vector. And this says if that is a vector input, these are the weights, W0, W1x1, WDXT. That is your output Y. So we say Y is equal to W transpose X. So linear regression problem is to find these weights W0 through WD for a given X. That's the learning problem, is to figure that out. And sometimes we use what are called as basis functions, phi of j. We say that y of xw is written as j equal to 1 through m minus 1. The original dimensionality of this space was d. We are converting it into some typically a lower number of dimensions, m dimensions we say. And we are saying it consists of these weights associated with a bunch of basis functions of these. So we have raw inputs x, and we're going to convert these raw inputs x into some smaller set of features. And there are going to be m, the input may have d dimensions, maybe d pixels, that could be 1,000,000 pixels. I'm saying, can you convert it into maybe 100 features? So that would be m. And these are the values, phi j's are the values along each of these features for this raw input x. And this becomes the weights over here. So the problem now is stated not in this way, but in a different way. These w's are different from these w's because they're dealing with the feature vectors here, which are much lower dimensionality. But it's got the same form. It's just a bunch of additions. We call it as W transpose X here. Now it becomes W transpose phi of X, right? Okay. So linear regression problem is to find these weights. And we end up defining a loss function as to, well, how are you going to find these W's? What is your criterion? We say, well, you minimize this sum of squared errors. And we say this is, what is output for the W? Tn is the example value. T's are target values, right? So for each xn, there is a Tn. So for this input, there is an output. And the difference between the output, y is the model. We call it as a model output. What the model is outputting and what it should have been its value. We take the square difference between the two, add them all up, and we kind of associate with it a 1/2 in the front here. The reason we put a 1/2 in the front here is arbitrary, but it makes our life a bit simpler, because this is the loss function, and the summing is happening over a bunch of samples, n samples, and we are saying this quantity should be minimized. And to minimize this quantity, this loss function, the way to do it is to take its derivative, which means this 2 is going to go up front when you take the derivative. You got to remember that what is the derivative of x squared? It becomes 2x, right? So that 2 and this 2 cancel off. So you get in the derivative a simpler form of it, which is simply the sum of all the differences, interestingly, the derivative here of all the model outputs and the targets. And we say that is going to be the value of the derivative of this loss function. And what are we going to do with that derivative is we use gradient descent. If you recall, we talked about the derivative is taken and we subtract it with a learning rate from the previous value of W. That gives you a new value of W. Hopefully we're heading in the right direction by that approach, by taking the negative of the derivative. There's one more term here that's hanging on, which is lambda over 2 times W squared. These vertical lines here are exactly what we just defined, called the norm. This is when we write it like this, it's a squared L2 norm, squared norm, okay? So this is computing the distance of the weight vector, and we are taking the squared norm here. And we are giving some kind of weightage to that. So we say the loss function is not just minimizing the sum of squares, but also minimizing the length of the weight vector. Length as measured by the squared Euclidean norm here. And why do we put this one? The first part is easy, right? It's about, maybe it's easy if you look at this example. This is an example of linear regression. This involves only one input and one output. Okay, and this has got D inputs in general. Only one input, one output. These red points are all the samples we've got. So for each input, what is the value of the output? And linear regression is saying, find me the best straight line to fit it. And that straight line is going to be characterized by a perpendicular to it from the origin. And that is a vector. And that vector values correspond to the weights associated with this particular line. Usually a line in a space is specified by a perpendicular to that line from the origin. And that is a one-dimensional example. Here is another example where we have, this is also a one-dimensional example. The input is 0 to 1, a value of x. And the output is sine x. Sine x is this green curve, perfect, sine x. But we don't know what the function is. We are given a bunch of samples and asked to predict what is the best fit. In this case, a linear fit won't do a good job here because it'll just give you some straight line that's fitting it. We need what's called as a polynomial. This is going to be a polynomial fit. A higher degree polynomial is going to be needed. So we refer to this W squared. This term is an important term actually. It's called as a regularizer. So an important concept in machine learning is called regularization, which sounds like a nuisance term. You're trying to find a fit, and you're tagging along with a whole additional term. So this says not only should we minimize the difference between the output of the model and the output is supposed to be. So it's also go along and make this W as small as possible in the space of all possible weight vectors W. Why do we do that is the regularizer controls the kind of fit you're going to get. A kind of fit that you might otherwise end up is going to be, for example, in this polynomial case, if it allows a high degree polynomial, it's going to give you a solution that runs through every single point perfectly. That's going to be a high degree polynomial that's going to be kind of oscillating all over the place. And that's going to be a very poor fit because as you can see, the data came from a green sinusoid and doesn't require a tremendous amount of variability in it, and you need to control it. And one way to control it is by minimizing the norm of the weight vector. Of course, I've not explained fully why that happens. Maybe we'll encounter it a bit later. But this is a most common, this is called as a norm penalty. So it says you must find an answer, but you must also keep your weight vector controllable. When we do linear regression more formally next week, we'll again encounter this problem, and I will talk about what would happen if we didn't have that regularization term, and you get all these crazy solutions. This is in this polynomial case, and that won't be generalization. An important concept in machine learning is called generalization. That is, you're not just trying to fit the curve perfectly. We are actually trying to come up with a solution that's going to fit samples you have not seen before. Sounds like a strange thing. I give you a set of samples and ask you to learn something, and then I'm going to test you on something you have not seen before. I guess that's how our quizzes and exams are, right? We don't give you exactly the same problem that was done in class and give you a new problem. And which means we're testing you on whether you have understood the concept rather than memorize the exact solution to a given problem. And that's exactly machine learning. And the way to achieve it is mathematically not just to fit it exactly to the data, but also to control something else. And there are a dozen or more methods of regularization. One of the important research topics in machine learning is regularization. Norm penalty is one of the important ones, but there are so many other methods. Okay, so anyway, today I think Mihir is going to be covering more of this stuff, which I'm happy about. He's going to do closed form solutions to linear regression problem, and yeah, this slide nothing much here. LP norm and distance. Norm is the length of a vector. And we can use it to draw a unit circle from the origin. Sure, that's not a surprising thing. Distance between two vectors. Distance between two vectors is p minus w. If I give you two vectors in any dimensional space, it is difference between the two vectors, and we take the L2 norm. L2 norm is what? Square root of v1 minus w1 squared, vn minus w1 squared. And so this distance to origin would be just the square root of the sum of squares. That was what we saw in the previous slide. Origin would be all, one of these vectors is all zeros, and any other vector would be just square the terms and add them up. So that becomes the length of that vector, which is exactly what we used in the previous slide. Oh, there are so many other concepts. So we know how to measure the length of a vector. If I give you a vector and you say, well, I can tell you what is the length of that vector. And if I give you a matrix, we can also give a number which tells you something about the matrix as opposed to a vector. And one of these is called a Frobenius norm, which is taking the squares of all these elements, adding them all up and taking the square root of that is referred to as a Frobenius norm. And why is this useful? This is a term you won't find in a linear algebra textbook in mathematics course, right? I mean, if you took linear algebra in the math department, you will learn what a norm is, but you won't learn what a Frobenius norm is. Maybe they have it nowadays, but this is something useful in machine learning and deep learning. So they defined it. I guess Frobenius must be a mathematician who might have thought of this first. So we're saying in the layers of a neural network involve matrix multiplication. We're going to be multiplying each layer by another matrix. And so we would like to have a regularization term there also, which maybe minimize the Frobenius of weight matrices over L layers. So we're going I equal to 1 through L for layer, and Wi, which is written like a norm of this. We're talking about norm of this matrix, not norm of a vector. Normally, norm is defined only for vectors. We are defining a norm for a matrix and putting an F on it. That's the Frobenius norm. What is Frobenius norm? It is this quantity here, Frobenius norm. And so we call that's a scalar quantity, and minimize the Frobenius norm over L layers. And there's some other additive term over here. So anyway, it gets its use in, this is a very specialized kind of norm, which is only used in these deep learning situations. Saying, what are you trying to do? Well, we're trying to find the weights in this neural network that's going to recognize my cats or dogs extremely well. And we need to choose the weights of the matrices. And how are we going to choose the weights? We're going to choose it such that it minimizes the error. Surely, it shouldn't be a dog for a cat. But also we add a regularization term, which says, while you're doing it, find me the values that are going to keep this W as small as possible. Okay. And so that's again another concept. And this is another useful thing to have in your toolbox. How do you say two vectors? How similar are they? We see that you can think of any million pixel image off of your camera as a point in a million dimensional space. Okay. And then I give you a picture of one is a picture of a cat, and the other one is a picture of a dog. A and B, and then I ask you how similar are A and B. Of course, if A and B exactly fall at the same point, then you say, oh wow, they are there's no difference. So A and B are exactly the same. But you know, cat and a dog are not going to be falling at the same point. They're going to be different. How different are they? Well, it's a very clever way of measuring the similarity of two vectors. And one of them is simply based on the idea of a cosine of the angle between the two vectors. So you take the angle between the two vectors and take the cosine of that. And if you remember cosine of 0 is equal to 1, right? Maybe you remember that from trigonometry. Yeah. Cosine of 0 equal to 1. So what it says is, if the two pictures you have are exactly the same, then the cosine of the two, the angle between the two is 0, which means the similarity is 1. That's the maximum value cosine can have. Right? The minimum value cosine can have is what? 0? Or is it minus 1?
Minus 1.
Hmm?
Minus 1.
1. Okay. All right. Somebody said minus 1. All right. We'll take you at that. So cosine can be if they're very different or so on. So cosine is some measure of the similarity. And so it says interestingly, the dot product of two vectors can be written in terms of their L2 norms and the angle theta between them. Wow, isn't that cool? If I give you two vectors, A and B, and I take the dot product as a scalar vector, scalar product we call it. So multiplying the two vectors gives you some value, some number you're going to get. And that number is going to be exactly equal to the L2 norm of this. What is the length of this vector? That's a scalar. What is the length of this vector? That's a scalar. Multiplied by the cosine of the angle between the two vectors x and y. Well, how do you measure cosine? Cosine between two vectors is a measure of their similarity. And similarity equal to cos theta is equal to A times B over the norm of A times norm of B. And so this is summation of AI, BI, corresponding elements. A, B in this case are vectors. And then you have square root sum of squares, square root of sum of squares. Okay, that's the definition of cos theta. The cosine of the angle is written like that. And so it says, you can compute the angle like that, and then you multiply these by the norms. I guess this is again being used, the same norm idea is used being in this definition as well as here. So this is the dot product two vectors can be written in this way. So in a way, but the distance is given by cosine. The cosine is similarity. Similarity and distance sometimes are inverse concepts. If distance is high, similarity is low. If similarity is high, distance is low, that kind of a thing. And so when we get cosine of theta equal to 1, which means it's perfectly similar. And so I guess, yeah, in this case, there's no reciprocal relationship. So cosine maximum is 1, similarity is 1 for that. And then any other setting becomes smaller. So something that is useful because the world is full of vectors, and you're frequently called upon to say, how similar are these two things? The cosine is a very quick way of computing that value.
Professor, sorry to interrupt. There's a question in the chat box by Gaurav. Um, he asks whether the norm is the same as normalization.
Oh, okay, no. Okay, that's an interesting question. Norm and normalization. Okay, on the face of it, they're absolutely unrelated. Norm, it comes from linear algebra, norm of a vector, which is the length of a vector. I don't know what the etymology of it is. How did they come up? Why did they come up with the word norm to measure the length of a vector? So it is a very specialized technical term coming from linear algebra is a norm of a vector is the length of the vector. I don't know how that word was chosen to be. Right? That's an interesting question. But normalization is a very colloquial term. You make normalized things, and we encounter that in machine learning quite a bit uh, by saying, okay, take the neural network we talked about to recognize cats and dogs. The last layer of the neural network sums up all the values and the corresponding to each of the choices. It is adding them all up. It's giving you a score for every one of them. And then we say, look, we got, for the cat we have the value 758, and for dog we have the value of 635, and so on, some big numbers like that. Normalization would say, tell me what the values are between the range of 0 to 1, and that they should all add up to 1. So we use this thing called a softmax. If I give you a set of numbers and I want to get values between 0 and 1, assigning higher confidence to higher numbers, we take the e to the power of each of these values and divide it by sum of e to the power of each of these values. And we say the denominator is a normalizer. It normalizes it to lie between 0 and 1 and add up. So we call that as a process of normalization. That has nothing to do with the length of the vector, all right, on the face of it at least. So there might be something subtle that might be happening, but not as far as I can tell. So norm and normalization are very different concepts. Okay. All right. Any other question? All right. Shall we move on? I think.
So there's one more question, Professor, by Yusuf. So he asks for calculating the norm, which is LP norm, for finding the P norm. Does P relate to the dimension of the vector?
Oh, no. The LP norm, that's the general way of measuring distance. So L1, L2, L3, L4, L infinity, right? These are all special cases of the LP norm. And the question is whether, the question I'm trying to answer is whether P has anything to do with the dimensionality of the space. That's an interesting question, but I don't think so, no. Invariably, we use the L2 norm. The L2 norm kind of pops out. It's a very natural choice, actually. I mean, it pops out in Pythagoras Theorem, right? Pythagoras didn't say the cube on the hypotenuse is equal to cube on the sum of the cubes on the sides. No. He said the square on the hypotenuse is equal to the sum of the squares on the sides of the rectangle, of the triangle, right? Right angle triangle. And it's a very natural thing. It occurs in Gaussian normal distribution also. You only get a square. You don't get cubes. And you don't get L1 norm either. L1 norm also is a very peculiar one, but it's a very simple one to compute. And so it does get used. And so L1 norm is occasionally used. I would say 95% of the time we use L2 norm. And the other norms are hardly ever used. Okay. L infinity sounds interesting. Simply taking the max of a set of values and using that as a norm. Okay, so no connection between P and the dimensionality of the space. Okay, interesting question. Okay.
That's all the questions, Professor.
Those are all the questions. Great. Okay, I'm glad you're thinking rather than completely falling asleep, right? Okay. All right, so let's do a couple more slides if we have the time. So let's see. Diagonal matrices are important. It's a special kind of matrix. Diagonal matrix has mostly zeros with non-zero entries only in a diagonal. And this is an example of a diagonal matrix. If only they're all ones, it's called an identity matrix. And a matrix that is commonly encountered in machine learning is a covariance matrix, which is telling you what is the difference between, what is the dependency between different features, right? So if the features that you're using, features means, let's say the pixel values, or maybe higher order features that are not just pixel values, but you're computing the presence of a straight line, presence of a vertical line, horizontal line, curved line, a closed area. Those are all features that could be computed from the basic pixel values. Let's say we have a black and white image of a hand drawing or a handwritten 6 or 7. So we could be computing what kind of strokes there are in writing that 7. We say there is a horizontal stroke on the top and nearly vertical stroke also. So we say you can compute presence of these kinds of things, those become features. And if those features are all statistically independent of each other, right? So this gets into the definition of independence, right? So the probability of one times probability of the other is equal to the joint probability of both. That's how independence is defined. We say two variables are independent. If that's the case, if they're independent, if all your features are independent, the dependencies, it means there are no dependencies, which means the entire covariance matrix, which consists of the variances, which are defined like this: covariance of xy, sigma xy, expected value of x minus mu x times y minus mu y. And that is, those are all zeros, and only the diagonal elements which correspond to the variances of each of these exist here. And we say this is a covariance matrix, and it's also a diagonal matrix. When you have a diagonal matrix like this, it means your data looks something like this. That the data along the dimension, there are only 2 dimensions here. They're all kind of nicely circular at all levels. This is the density. The density is very high in the mid. This is a normal distribution in 2 dimensions. The red corresponds to lots of points there, and then fewer and fewer points, and then fewer and fewer as you go out. So this is a Gaussian hill imposed on a 2-dimensional space, and we say this is a diagonal matrix also, right? So that's a special matrix encountered very often in machine learning. You might as well, get on top of what is meant by covariance matrix. Look at this. This is the equation here of a normal distribution, which also you should get familiar with. Normal distribution of x is a vector here, given mu. This straight line means given. Normal distribution is given 2 parameters: mu, the mean of the distribution, and this big sigma here, it doesn't mean summation anymore. Here it means, in this context, it's called as a covariance matrix. That is this quantity, this whole thing. And that is written as 1 over 2 pi to the power of 1/2, which is square root of 2 pi, times, this is the covariance matrix sigma sitting over here. These vertical lines in linear algebra terms is called the determinant of this matrix. I think we saw something about determinant earlier on. Determinant is again a single value that represents the matrix. And we take the square root, with this is the square of that determinant here in the denominator. And this is exponential of minus 1/2 x minus mu transpose. We saw what is meant by transpose. This is sigma inverse. Oh, wow. We're taking this covariance matrix, something like this, and we're saying, please compute the inverse of this matrix, running it through the inverse operation and put it on here. That is and then x minus mu again occurs here. So this is the formula for a multivariate distribution, which is nicely symmetrical like this. If you change the sigma to be non-symmetrical, the points are all going to be skewed. So if you have dependencies between different dimensions, let's say the 2 features here are very dependent on each other. If they're completely dependent on each other, it might be all on a 45-degree line. If both are the same, then all the data lies on a 45-degree line. They're the same features. They're not going to be spread around like this. But if there is some other in-between covariance, it might be an oval shape here, an ellipse here, and so on, right? So Mihir, are you ready or should I go on for a little while?
We can start the breakout sessions now.
You'll have the breakout session? Okay. All right. So hopefully I covered some stuff that's useful for you. All right. Or you can introduce them again. All right, everyone. So you are in capable hands of Mihir. He's working hard to teach you guys properly, preparing all these breakout questions and sessions, and also the challenging task of keeping up with what I am teaching, so that it's not totally orthogonal to what I'm doing. Also, he's also taking you closer to the real world of implementing these things. Okay. All right then. So I will disappear from the class, and Mehir is going to take over.
Professor, can you make me the host for this session so that I can make the breakout?
Oh, okay, okay. Before I go, okay, let me just close my PowerPoint here, and I will create the breakouts for you all. And,
so, Professor, can you make the before breaking out the rooms? Can I just go over the problem
oh, you need
statement
to share
once?
it. Yeah, yeah. I don't know why it's not okay. You're going to share. Yeah, I want to look at your questions.
Okay.
So, share screen. Okay. All of what's share screen. Okay. Okay, you should be able to share it now.
Okay. Can everyone see my screen? Okay.
So you have 5 questions here.
So I have 5 Python notebooks, which has the 5 questions. So I'll just
5
go over
notebooks.
the
Okay.
first. Yeah, the first question. So the first team will be working on the air quality data set, and the data set has 788 instances and 14 attributes, including the target variable. So the task is to implement a linear regression model using the closed form solution for predicting the air quality index for Seattle City. And the
It is pretty
description
bad
of,
right now. Air quality index with all the fires going on there. Yeah.
yes.
Okay.
So yeah, so we have 13 attributes and 13 features and one target variable to predict. The target variable is the AQI, the air quality index. So what you have to do is, given the 13 features, you have to predict the air quality index for Seattle. And how would you implement the closed form solution is by using the Genesis equation. The Genesis equation is basically y equals x time input times the parameters. And if you want to find out the parameters w, what you have to do is basically pre-multiply your on left hand side and right hand side with x inverse, and that's how you get basically the parameters w. But the problem here is your input x is not a square matrix which has a full rank, so x inverse is intractable, and hence we use Moore's-Penrose pseudo inverse as a generalization of the matrix inversion for x. And the final solution that we reach to is this solution, which is x transpose x inverse times x transpose y. This will make sure that you get the parameters w. Once you get the parameters w, you basically have to test your model using the parameters w that you get. And for doing all this, you're not allowed to use the linear regression sklearns library, or you have to use the NumPy library, which helps you find the inverse in this case for pseudo inverse. And you can also use NumPy dot or multiply library, but you cannot use the linear regression library directly. And the steps that we have already implemented and given to you are the first 4 steps of importing the data set, partitioning the data set, scaling the data set, and um, giving you the labels. Your task is basically to implement step 5, 6, and 7. Step 5 is basically how would you calculate your parameters w. Step 6 is to use the parameters w on your test data set, and then finally calculate the root mean squared error using the equation as shown. So each team will be working on a different data set. So for example, the team 1 is working on um, the air quality data set. Team 2 is working on COVID. Team 3 is working on forest fires in California. Team 4 is working on the house price prediction. And then Team 5 is working on the Facebook comment volume data set. So all the data sets are interesting to work on and has different number of attributes and different number of instances. For example, team 5 has over 40,000 instances. So as you can imagine, with increasing number of instances, your size of input x will increase, and hence finding the pseudo inverse of x will be also difficult, and it is a time consuming task. So you can get started. Make sure that only one person from your team edits the Python notebook, or else you find errors while saving the Python notebook. And yeah, one person can share the screen and edit and make the edits, and the other team members can discuss and come to a right solution. So yeah, let's get started. Professor,
You want me to create the breakout rooms? Yeah.
yes.
All right. 5 rooms, right? Yeah. 11 participants per room. Okay.